Swayam Prabha. Digital India. Educated India.
In the last module, we looked at few acoustic quality indicators which included indicators of background noise level. We also looked at major component which is called reverberation time. We have few more indicators which we will address in the current module. These are measures for audibility information, how much audible the information is, that we will look at audibility of a particular information. Then we will talk about an important factor called room modes. Audibility of a particular speech or music depends primarily on how well you are able to hear, depends on, or it can be determined by rather 3 parameters. More or less they are the same, the indicator or the representation is also similar, but it considerably varies from one another. First is the articulation index, second is speech intelligibility index, third is speech transmission index. There is a another version of it available called RASTI, this is commonly termed as STI. There is another version called rapid articulation speech transmission index, RASTI. Then you have an indicator called clarity. There are more indicators, I have only chosen 4 of these things to talk about. There are also indicators like definition, envelopment, there are factors. First let us look at more clearly into these factors first. Articulation index, it is used for finding, it was intended or originally developed to study the sound privacy and intelligibility requirement in open office spaces. There are 2 things you have to understand, one is sound privacy and second is intelligibility. Say for example, if you are talking about an office space, you have open office, open plan offices, or you have private offices, private cabins versus a lecture hall. Here you will require acoustic privacy, say whatever a person talks to the other, there is a conversation or maybe there is a telephonic conversation, there is a discussion happening. The main criteria here is to make sure this conversation is not heard to the next person. Why I specifically point open offices, this is one of the most challenging spaces for designing acoustical, for doing acoustical design. You have an open space where people are sitting and you have to ensure that there should be only minimum amount of information which passes from at least one cubicle to the next cubicle. So the height of the partition matters, the kind of absorption you provide in the cubicle itself matters, then the type of false ceiling, the floor, all these things affect the acoustical quality of open offices. Most common problem, if you sit in an open office, say 50 people are sitting in that particular hall, you will have telephones ringing, you will have personal conversations, phone conversation, one-to-one interactions, people walking around, even the footfall sound. Lot of noise will be created and it is a single hall without much of barricades, so it will eventually spread out. So the main challenge is how do you arrest this? You will have to ensure acoustical privacy. On the other hand, if you look at a lecture hall, the intention is the signal has to reach them in the fullest possible manner. So you have to ensure the intelligibility. Whatever the speaker is talking about, he is addressing in full form, maximum possible without losses, it has to be delivered to as many ears are available in the hall. Articulation index was one of the attempt to decipher and translate the intelligibility and privacy requirements for open offices. Primarily it started there. It is actually the ratio between the voice level and the background noise. More or less these quality indicators, if you see, they will be a factor of S by N, that is signal to noise. Even articulation index, it talks about the voice level which is a signal and the background noise level which is a noise. So this is a form of signal to noise ratio. A minimum distraction, for example, it ranges from 0 to 1 articulation index, it ranges from 0 to 1. 1 means perfectly audible, 0 is you cannot hear, there is total inaudibility, which means acoustic privacy. So minimum distraction, for example, corresponds to an articulation index of 0.35 or lesser. If it is 0.35 or less in terms of articulation index, you are kind of assuming that, or you can ensure that you have attained acoustic privacy in a particular space. Then if you want confidential privacy, say if it is a boardroom where financial discussions are made, you might have to ensure a total acoustic privacy, which means you have to go as low as 0.1 or further low. Acoustic insulation plus absorption, both things are required, sound insulation as well as absorption of the emitted sound. If it exceeds 0.4, it means there is no acoustic privacy. Speech intelligibility is more or less similar to articulation index, but it has certain revised frequency weighting, and also it includes the effect of one frequency band masking the other frequency. Different frequency band sound is emitted, it includes the masking effect of one over the other. It is an improved version of articulation index, but the number also varies from speech intelligibility index also varies from 0 to 1. 0 means completely unintelligible and 1 is perfectly intelligible. Say if you are talking about speech intelligibility index in a lecture room, you will expect something above 0.8 or 0.9, the better it is, which means the speech is intelligible by 80%, 90%. Whereas if you are ending up with an SII of say for example 0.4, which means the intelligibility is very poor, only 40% the sound is intelligible. It will create more strain on the speaker side and it will result in less understanding or intelligibility from the listener's perspective. This is the same office that I showed you, we took measurement in different locations. The speech intelligibility varied somewhere between 0.35, some places it went close to 0.6, which means the acoustic privacy is less except for few spaces. Here the green band indicates there is a confidential privacy, which means the articulation index or speech intelligibility index is pretty much low, less than 0.1. If it is somewhere around 0.2 or lesser, you call it normal speech intelligibility or you have normal privacy. This is confidential privacy, this is normal, and if it goes above, the conversation is going to be intelligible. A better understanding of it, you can look at it. You can leave this column for now. This is articulation index AI. Speech intelligibility will be slightly higher than articulation index, the numbers will be 1 to 1, it will be slightly high. Say if you say it is above 0.65 or speech intelligibility is above 0.75, it means good communication. So whatever is spoke is being understood by the other side. It is necessary when communication is desirable. Imagine you are in a conference room. In the conference room you need a good speech intelligibility so that interpersonal conversations can be understood well, whereas between a conference room and the neighboring room or the cabin or an open office you need a speech privacy. The signal should not be spilling over, so that you ensure there is no overhearing of these conversations, or one is not disturbed by the other. It is both way. If the open office is very noisy, you have to ensure speech privacy here. So the speech intelligibility or articulation index has to come down. Say greater than 0.4, there is no privacy. On the other side, if you come as low as 0.1 of speech intelligibility index, you have confidential speech privacy. You also have to know, even at 0.1 or lesser speech intelligibility, the person is aware that there is a conversation happening. It is not a blanket insulation. You are aware that there is some conversation going on, but it is not intelligible. That is exactly what we are talking about here. We are not talking about a total zero proofing here. You are able to know that some conversation is going on, but you will not be understanding what it is. Whereas if you go to 0.2, 0.3, occasional intelligibility, work patterns are not interrupted. Whereas if you talk about say 0.35 or 0.45 of speech intelligibility index, you can hear and understand what the neighbor is conversing. A common phenomena you find in open offices. You are easily able to hear what the fourth or fifth cubicle the person is talking on phone. It is clearly audible, which means speech intelligibility is relatively higher. As a acoustic designer, you will be expected to bring these things down in open offices. How are these things measured? These are not directly measurable with instruments, but you have to conduct something called speech intelligibility test or articulation tests. Typically there are sets of words, common reference textbooks, guides would give you these kind of words. They are more or less sounding similar, say for example barb, barge, bark. So these are kind of the stress is same, coon, coop, cop. If the speech intelligibility is good, you will be able to understand each of these words and write it down. These are typically a announcing kind of tests, where dictation kind of tests, where a person dictates these words and the audience, they are asked to write down these words, or in some cases if you are doing for example the speech intelligibility test with kids, you cannot ask them to write these words. For example, you can give them pictures, you ask them to tick, but you spell the word, you ask them to tick the corresponding pictures. Then you determine how much percentage of what you said has actually reached them. Similarly for halls, for offices, you do this intelligibility or articulation tests, you spell these words. With now new electronic certain things you can also measure it, but the typical conventional way of doing it is to do this articulation tests, where you spell the words, then you start plotting it. There are three things, three levels in which understanding happens. First is the syllable level understanding, next is the word level understanding, and next is the sentence level understanding. You start plotting this, you see how much percentage you say unsatisfactory, poor, satisfactory or good, or if it is more than 95%, it is an excellent listening condition. That is, intelligibility is more than 95%, it means it is an excellent listening condition. You can do this for syllable level, word level and sentence level. As I said, the intelligibility as it increases, it goes from unsatisfactory all the way to an excellent listening condition. Another thing is speech transmission index, which we talked about, STI. This also ranges from 0 to 1. If you look at it, 0 which is bad, on the other side you have 1 which is excellent. It is similar to articulation index or speech intelligibility index, but different in terms of the index or the number range 0 to 1. It is also a range 0 to 1, but it differs considerably from articulation index and speech transmission index. It considers room reverberation into account in its calculation. This is one primary difference between articulation speech intelligibility indexes and the speech transmission index. While you have to do the dictation tests for determining articulation index or speech intelligibility index, STI or speech transmission index can be directly measured with instruments, or it can be laterally derived with certain measured parameters. Say if you know the reverberation time, if you know the frequency, then you can actually determine through certain calculations. I am going to show you. Using that you can determine what is a speech transmission index. It is measured between primary importance is given to 125 hertz to 8000 hertz. Another version of it, a rapid speech transmission index, it is a modified version of it, primarily used in lecture and amplified sound systems where they are used. You use rapid speech transmission index in place of standard speech transmission index. Both are more or less similar, just the numbers would vary. How do you determine RASTI? For example, RASTI is more commonly used index. RASTI is signal to noise ratio apparent. There is a relation here. This you get signal to noise ratio, you get from an index called modulation reduction function. This modulation reduction function depends on the reverberation time and the frequency, apart from the basic signal to noise ratio in that particular frequency. So every specific frequency you determine this modulation reduction function, then you find out what is the apparent signal to noise ratio. With that you can actually calculate RASTI. Similar formula is there for speech transmission index also, more or less the same formula applies there with a minimum little bit of modification. So we talked about articulation index, then speech intelligibility index, and then speech transmission index. Let us look at clarity of sound. These are certain common terms, but they have a lot of meaning in terms of acoustical design. Before we get into defining clarity, you take in x axis I will have time, here in millisecond. Last time we started with millisecond, went back to second. Let us now stick to milliseconds. This is as usual, this is sound pressure level in decibel. Imagine there is a trigger, there is a cracker, firecracker or an impulsive sound. This is a first instance, say this is 0, point number 0. From here there will be some amount of time related with this figure. This is a direct sound, the source and the receiver are here. So from source to receiver it will take some amount of time to reach. So this will be the direct sound. Imagine the sound is emitted somewhere here at 0.0 millisecond. If you take that as a cutoff, the person will hear the sound after this. So let us take that as a first point. Now there will be reflections happening. So imagine you have a floor plane, the first reflection, the sound which is directly emitted here gets reflected on the floor and then hits the person again. So you start hearing this is R1, this is direct, this is D which is indicating direct sound, this is R1, that is the first reflection. Then you have a ceiling, slightly tall ceiling, then the sound goes up here, it comes back. After a while you start hearing reflection 2. Similarly you have side walls, say for example in plan view this is a source, this is a section, this is a section. Say if you take a plan view you have a wide wall, so this is a direct sound, you had the floor and ceiling reflection. Then you have, this is in plan, you have R3 reflection 3, you will have R4. So many reflections would happen. Then there will be a reflection from the rear wall, so it will hit the rear wall, it will come back, R5. So many reflections would happen. As and when additional sound will come, this will be adding up, followed by R3, R4, R5, it will eventually decay down. Now whatever sound which is reaching your ears before 50 milliseconds, there are two thresholds we are talking about, 50 milliseconds and 80 milliseconds. Whatever sound reflections which are reaching you before 50 milliseconds would actually reinforce the original sound. Human ear will not be able to decipher which is the original sound and which are the reflections, because before 50 milliseconds, before you recognize and respond, they will actually come to your ears, which means they are actually reinforcing the original sound. This is for speech performance. When somebody is talking, say if it is a classroom or a lecture hall, you take a threshold of 50 milliseconds, which is really useful reflection. Like I said earlier, some reverberation is needed. Initial reflections, these are called initial reflections. Initial reflections are useful. These reflections will in fact help reinforcing the original sound. So the direct sound does not seem like a very dry phenomena. Whereas if it is for music, some instrument is played there. For musical performances, you take a threshold of 80 milliseconds. Before 80 milliseconds, whatever sound comes to you will reinforce the direct sound. You will not be able to distinguish between the direct sound and the reflected sound. You will also ensure the continuity, the first syllable versus the second syllable. Say if somebody is reciting a poetry or if somebody is playing a wind instrument, the first spell versus the second spell, it will ensure there is a continuity of sound. So sound is not a direct distinct set of signals, rather it becomes a continuous waveform, so you can appreciate the music much better. So 50 millisecond threshold and 80 millisecond threshold are important. Now let us look at the details of clarity in detail. Clarity, we are talking about 50 milliseconds, 80 milliseconds level. Let us first define what is clarity. Clarity is the total amount of sound energy arriving before certain threshold. It can be 50 milliseconds if you call it C50, it can be 80 milliseconds if you call it C80. It is actually the ratio between whatever sound signals arrive before 50 milliseconds or 80 milliseconds and those which are arriving after that. So, initially we talked about late reflection, initial reflections, you have late reflections. This you refer, initial reflection you refer as useful reflections, this need to be avoided. Actually clarity will help you attain or distinguish between initial and late reflections. You have certain thresholds, how much clarity is allowed, you know, in terms of C50 or C80, we will look at it. Primarily we estimate between 500 and 4000 hertz. The formula is very simple, E is a sound energy. If you say C50, it is energy which is arriving within 50 milliseconds. This is the whole energy which is arriving. Infinity actually means you are taking a longer time domain minus the 50. So, you are actually subtracting this, this goes to the numerator and whatever comes after this goes into the denominator. It is expressed in terms of decibels, again 10 log of the initial energy 50 millisecond within that and the late energy. Similarly, clarity of 80 initial versus the late. This is a crucial factor which will actually help you improve the acoustic performance of the hall. Even if reverberation time is within limit, you have attained a reverberation time of 1 which is permissible, for example for a lecture hall or a multipurpose room. You have to keep in track of what clarity you are attaining, which is an additional implication or additional indicator rather for the acoustical performance of a particular space. The same hall that we talked about, the circular, you know, hall which we were seeing in the previous example, we determined the clarity. This is at 500 hertz, as I said it is in decibel. Clarity, you have speakers here, there is one set of speakers, there is one more set of speakers in this, this is a podium, people are seated here. So, the clarity actually varies with respect to position considerably. Imagine you are sitting close to this in the speaker's throw, the clarity is pretty high, 2.93, which means it is okay. See, essentially it is a signal to noise ratio, 0 or minus negative number indicates the noise is more, signal is less, which is not preferable. In these areas the signal is strong compared to the noise, so more or less your clarity values are okay. But if you go towards the periphery or in the center areas, you are coming close to 0 or sometimes negative values, which means the noise levels are more compared to the signal itself, which means you have to start working out your acoustical treatment. There is another parameter which is called articulation loss of consonants. English specifically, you know that vowels and consonants are there, vowels are more strong. If you are talking just pronouncing A, E, I, O, U, the words, the syllables are not lost much, whereas consonants are more softer, you will incur lot of losses when you spell consonances. So, acoustic quality is also indicated in terms of the loss of consonants. So, when a person is talking, how much amount of consonants are lost? For example, if more than 11% of consonants are lost, which means it indicates poor intelligibility. When the consonant loss is less than or equal to 3%, which means the intelligibility is ideal. You can somewhere target between 5 to 6 percentage or maximum of 8 percentage, it is still good. You can allow up to loss of 8% loss of consonants. This is another indicator. We are not getting too much into detail of articulation loss or alcons commonly referred to. The other 3 parameters are very useful indicators. Later one of the following modules I will show you or demonstrate one example of an actual auditorium where these parameters were tested and measured. I will be showing you through a demonstration how these parameters varied. The next crucial thing which one has to understand is the term called room mode. Room mode is actually a reflection phenomena. If you have a particular room of this, so you can think of the same 4 meter by 4 meter room that we were talking about. You have a sound source, then when these parallel wall surfaces are really reflective, certain frequency, again when you talk about room mode, it is very much frequency dependent, it is highly dependent on the frequency and it is also dependent on the room proportion, that is the height, the width length of the room. These are very crucial determinants of whether you will incur room modes or not. They occur primarily in low frequency range, especially in small rooms. If it is a huge auditorium, or if the room is primarily used for mid and high frequency range sounds, you may not be facing problems with room modes, but whereas recording studios or very small rooms, you will actually be finding room modes as a problem. You have a term called standing wave. Do not cancel each other when you have specific thing. Just take a cross section, you find that there is a source here and there is the other wall surface. You have these particular wave phenomena which is forming. It will actually disturb. This is a kind of resonant thing where it will not allow normal decay of sound, it will persist. The sound will not be decaying down as anticipated in your reverberation time calculation. RT will not tell you whether you will have room mode or not. There is a separate set of cross checking that you need to do. Depending on those things, you will be able to find whether room mode would occur in a particular space or not. In this case, a particular set of wave in a specific frequency might develop a standing wave. Standing wave is something which is perfectly fitting the peak to peak here. It may be 1, 2, 4, 5, it may be as many up to certain numbers. It may be just one wave, or it may be more in numbers also, but they do not decay easily. What happens, a specific phenomena, if you are a receiver, you walk along from this end to this end, you will find a minimum sound, say if the noise level from the source is 60 dB, at this point you may be experiencing 50, here it will again peak to 60 or 65 dB. So as you walk through, you will find 8 to 10 dB difference. I may be more exaggerating the numbers, but you will be able to find out a difference, starking understandable difference, perceivable difference as you walk from one side to the other. To give you a very simple form of representation, this would, imagine you are in a classroom listening. If you are seated here, the kind of sound experience and the loudness of the sound you experience in this point, say point A, would be considerably different from this particular point B. Here, if you are sitting here, the sound level would be much higher, whereas here the sound level would be lesser. This is exactly what we are trying to check. This is one common check which people do for smaller rooms, like I said, especially in low frequency ranges, in order to ensure this phenomena does not happen. There are different types of room modes. The one we were talking about is an axial mode, where it is directly the source and the listener, the source versus two parallel walls. There is a standing wave which is just stuck here, this will not decay that easily. Again, you can determine the dimensions, we will look at it shortly. As I said, it can be 1, it can be more in numbers, depends on the frequency and number of the distance, the width or length, whichever is shorter, it might happen, or it is proportional. There are tangential modes and there are oblique modes. It can also happen tangentially to surfaces, vertically or horizontally, or it can be oblique, happening all across in 3 dimensions. A simple formula would help you find out whether two things can be found out: at which frequency standing wave will form. For example, if you have a room of dimension, say 4 meter by 4 meter, you have this dimension, length, width both are same, you have the height 3 meters. Now you can substitute length, width and height. This will be mode number, which number of mode it is, the first mode, second mode. This is the velocity. If you find out, substitute this, you will be able to find out. Simple, if you solve this, say for one dimension, you forget width and height, since it is axial, let us take one by one. If you want to find out first in terms of the length, which is 4 meter, you will just have to say 172 by 4, which will give you the particular frequency at which standing wave might occur. Say somewhere close to 40 hertz, you will probably experience standing wave. If your room is meant for certain instrument which is playing a note at 40 hertz, you might experience a standing wave, which will spoil the whole appreciation of the music itself. In that case, you will have to provide treatment again in that particular low frequency range. So it also tells you which frequency you have to actually provide treatment for. As the room width reduces further, instead of 4 meter you take a 2 or 2.5 meter, then what happens here, say if it is 2 meter, you will have standing wave forming somewhere around 90 hertz, 85 hertz, somewhere close to 86 hertz you will have standing wave, which means as the room width comes down or the height comes down, any dimension of the room comes down, you will start experiencing room modes at slightly higher frequencies, whereas if you have wider rooms, the room modes occur at very low frequency, marginal. Say instead of 4 meter room, you imagine a 10 meter room, the room mode, probably the first mode which can happen would be somewhere around 17 hertz, which is more or less which your ear cannot detect. So it is not a really crucial thing, whereas if a room mode is occurring at 100 or 125 hertz, it will be a crucial thing to address. There are specific nomograms with which you can find what is the appropriate size proportion of the room, simple ones, x and y dimensions, it will tell you in which region the room mode would occur and how do you avoid it. These are called Bolt's criteria. It also varies with volume and frequency. A simple thing, a reference chart with which you can actually determine whether my room ratio, say if it is 1:2, 1:3, say 4 meter by 8 meter room, 1:2, whether this ratio is okay or not. If you have to adjust this, then you will have to say, for example, since here we were talking about only axial mode, so 2 of these things were negated. Instead, if you are talking about a oblique mode, all the 3 frequencies will come into picture. So 1 by length, 1 by width, 1 by height will give you the first oblique mode. As it goes on, it will increase. Eventually the frequency of occurrence will also vary. So appropriately you can determine using these nomograms what is my perfect room ratio, height to, say for example, width, length to width. How do I determine this? Nomograms will help you understand. To give you a quick recap of what we studied now, we studied about certain acoustic quality indicators which we left in the previous section. We started with reverberation time, we stopped with reverberation time in the previous section. Today we looked at articulation index, speech intelligibility index and speech transmission index as well as RASTI. Apart from that, we looked at a phenomenon called room mode, which is a crucial thing for smaller rooms and in low frequency sound pressure levels. Thank you.